This discussion is about the rate of change. There are two types of rate of change that we're going to discuss here. First is the average rate of change, and the second is instantaneous rate of change. Let me give a kind of an example, and you see a graph that I've made here. We'll discuss in a moment. But average rate of change, if we're thinking about, for instance, speed is a rate of change. It's the distance as a change in time. The distance traveled as a change in time. So that velocity or speed is a rate of change. Now, the average rate of change, or the average velocity, or the average speed, we would look at the total distance traveled divided by the time it takes to travel that distance, and then we would have our speed. So, for instance, in the example that we see here, but that's certainly much different than the speed we're traveling at a specific time. And the speed we're traveling at a specific time or a specific instant is called an instantaneous rate of change. So the average rate of change is over the whole trip. Instantaneous is at a particular given time. So you see in the graph here, the horizontal axis is the time traveled in hours. So 1 hour, 2 hours, 3 hours. And the vertical axis is the distance traveled in miles. So 15 miles, 30 miles, 45 miles, and so on. So you can see after 1 hour, in this case, the car or the person traveled 15 miles. After 2 hours, the total travel distance was 75 miles, and after 3 hours, the total travel distance is 90 miles. So if we wanted to know the average rate of change, in this case, the average speed, or the rate of change, from, let's say, 0 hours to 3 hours. And it would be an easy, simple application. What we would find out is the total distance traveled and divide that by the time it took to travel, by total time. And so in this case, the total distance traveled from 0 hours to 3 hours, in that amount of time, that would actually, in this case, what be 90 miles traveled, and it took 3 hours. And so we know that that average then, of course, would be 30 miles per hour. Okay? Now, we can ask the question a little bit differently here. What is the average speed or the average rate of change? What's the average speed from 1 hour to 2 hours, that part of the trip? Okay, so you can see from this graph that we're changing speeds. Sometimes we're going slow, sometimes we're going fast, and of course that's the normal way things happen. So what we would look for is the distance involved from 1 hour to 2 hours. Well, at 2 hours, the distance traveled would be, at 2 hours, 75 miles. At 1 hour, the distance would have been, what is that, 15 miles? So what we would do is we would take 75, the greatest distance, subtract the smallest distance. So this is going to be the distance traveled, okay? This is the amount of miles traveled. And then we would calculate how long it took to travel that. Well, from 1 hour to 2 hours, that difference in time would be the total amount of time. Okay, well, this was distance, excuse me. And this is the time, and of course that's calculated in hours. That was my bad. Okay, calculated in hours. So 75 minus 15 is 60. 2 minus 1 is 1. And that would be miles per hour. Miles per hour. So we're traveling between 1 and 2 hours. The average speed was 60 miles per hour. You get that point. Of course, we could also calculate from 2 hours to 3 hours. Well, from 2 hours to 3 hours, we actually traveled from 75 miles to 90. So that difference is 15, and that's another hour. So it would have been 15 miles per hour from hour 2 to hour 3. Well, more generally, let me make this point. This is what it would look like more generally. Okay, if we had a graph, or we had enough information, and maybe this graph was the graph of f of x, and suppose this is where x is equal to a, and so we're talking about this point on the graph, and suppose this is where x is equal to b, and so we're talking about this point on the graph. Now, let's be clear, if this is the graph of f, then the point on this graph at this position, it has an x value of b and a y value that we get by putting b into the function. So that would be f of b. So that means this y value over here is f of b. Now, of course, this point has an x value of a. And to calculate the y value, we would put a into the function, and so that would be f of a. So this y value here is f of a. Now, if we kind of compare what we did up there, here's the definition. Okay, this is the way average rate of change is actually calculated in general. The average rate of change of f from x equal a to x equal b is calculated this way. We take the ending y value. In this case, it happens to be bigger, but the ending y value. So we're going from a to b, and so b is the ending x value, so f of b is the ending y value. So it would be f of b subtract the beginning y value, f of a. And we would divide that by the amount of change in x. And so the amount of change in x is the last b value subtract the first b value. And if you notice the way this compares to our example above, the f of b would have been the ending miles, the f of a would have been the beginning miles. So f of b minus f of a would be the number of miles. And b would have been the ending time, and a would have been the beginning time, and b minus a would have been the amount of time. So it's related to what we've already done. Now, I would also encourage you to recognize that this really looks like, see, this is similar to, if you will, we're not going to use this notation, but this looks like y sub 2 minus y sub 1 over x sub 2 minus x sub 1. See, this is the second x value on bottom, the b, minus the first x value on bottom, the a. On top is the second y value minus the first y value. And so we recognize this as a slope, don't we? So the bottom line here, well, we'll use this formula, but the bottom line is what's happening is if we're actually calculating the slope of the line that connects those 2 points. So the average rate of speed is actually the slope of this line. And this line is called a, oh, I'm sorry, I'm lost right now. Anyway, the slope of this line. it's called a secant line, my bad. It's called a secant line when we connect 2 points. The slope of this secant line is the average rate of change between those 2 points. We're not always using a graph to do this with, and we'll pick this up and see from further how we can take a problem where we don't have a graph and still answer these questions. Okay, we're going to look at a problem. You can see the statement of the problem. Find the average rate of change of f of x equal negative 2x squared plus 1 between x equal 2 and x equals 6. Now, of course, this is a problem that's not related to speed. It's just talking about the average rate of change of a function between 2 x values. So, if you will, let me call average rate of change, ARC, average rate of change. Remember, the way we set that up is it's f of b minus f of a divided by b minus a. That is, we have a first x value and a second x value. So the first x value is the a, there's a. Second x value is the b. And so f of a would be f of 2. And f of b, of course, would be f of 6. So to calculate this average rate of change, we need all of those values. So let's first calculate the f of a value. That is the f of 2. And remember, that's f of a. And f of 2, well, what is that? That's negative 2 times 2 squared plus 1. That's negative 2 times 4 plus 1, or negative 8 plus 1, which is negative 7. Okay, the f of b value then is f of 6. And so that's negative 2 times 6 squared plus 1. That's negative 2 times 36 plus 1. And that's negative 72 plus 1, which is what? Negative 71. Okay, so average rate of change. Then my other abbreviation. Average rate of change is f of b minus f of a over b minus a. And in this case, f of b we calculated to be negative 71. Subtract f of a, we calculated to be negative 7. Divided by b, which is 6, minus a, which is 2. And we see up here, negative 7 minus a negative 7, negative 71 minus a negative 7 is negative 71 plus 7. So what is that? Negative 64? That gives us a negative 64 divided by 4, or in this case, that calculates to what? Negative, what is that? Negative 16? I believe so. Negative 16. Now, you notice something a little different here is that we actually have a negative average rate of change instead of positive, which just means this changing in a negative way might have the idea of something decreasing as opposed to increasing. So that's what's happening in this case. And it's not a mistake. That's exactly the correct result. Now you can see the next problem we're going to work on. The concentration C of a drug in a patient's bloodstream is monitored in 10-minute intervals for 2 hours, where the time T is measured in minutes. And C, as you can see above, is milligrams per milliliters. So, of course, across the top we have time 0 minutes, that's the start of time, 10 minutes, 20 minutes, 30 minutes, and so on. And the concentration starting at 0, that's as the right as the drug is administered. And then we see that the concentration to 1737 goes up as we would expect time to pass. But now near the end, we see that concentration starts going back down. And that, of course, isn't surprising either. Concentration will go up and then go down. And here's what we're supposed to do. We're supposed to find the average rate of change over each of the intervals. Over each interval. And the first interval, okay, we'll call it part A. The first interval is the interval from 0 to 10. As we start this, we need to kind of put in context what we've already done. You see that here we don't have a function f, we don't have x's, but we can kind of relate to that. What we called x's before might be this value. That's a time idea. And what we called f of x's before, then the resulting of that time would be here. Okay, and of course, or we might call, and of course as before, what we saw is this was actually the A value, the beginning X value, and this was the B value or the ending X value. So what we really, another thing we kind of need to keep in mind is the average rate of change basically is the change in C in this case, the change of C divided by the change in T. And sometimes we call that delta C for change in. So in the next problem about average rate of change that we want to look at has to do with a free-falling object. And actually, in this problem, we don't really need to know this, but this is as if an object was dropped off at 100-foot height and is going to the ground. And so what models that is h is equal to negative 16t squared plus 100. So what this means at time t, okay, and t is measured in seconds, then the height the object is from the ground, the height from the ground is calculated, is determined by h. Is determined by h. And h is measured in feet. Okay, so here's what we're to do. Find, start out with A, find the average velocity, and we're thinking of velocity, of course, as a rate of change. Average velocity from 1 second to 2 seconds. Now, let's put a little information together here. In our model, we're letting time go by, and we're getting a height from the ground. So for instance, at time equals 0, we'll calculate height by saying, oh, that's negative 16 times our time of 0 plus 100, which is equal to 100. So at time 0, we're 100 feet off the ground. And that's what I was mentioning a while ago. This is being an object being dropped from 100 feet up. After 1 second passes, then we would calculate the height off the ground after 1 second, and that would be negative 16 times 1 squared plus 100. And I see I wrote this equation down way up here incorrectly. That's a negative 16t squared. So in this case, we calculate that to be negative 16 plus 100, which is what, 84? And in a similar fashion, we could calculate the height after 2 seconds, and you see the way that calculation is going. It's negative 16 times 2 squared plus 100. And in this case, that'll be negative 64 plus 100. Okay, which ends up being 36 feet. So after 2 seconds, it's 36 feet off the ground. So you can see that it's traveling faster between 1 and 2 seconds as it did between 0 and 1 second, because it traveled a lot further. So here's the problem. Oh, we already have the problem stated there. Find the average velocity. So what we really are looking for the average velocity here, well, to calculate the velocity, it's going to be the change in height divided by the change in time. And we're talking about between 1 and 2 seconds. So the idea is at 2 seconds, we're 36 feet off the ground. Minus at 1 second, we're 84 feet off the ground. Okay? And we're going to divide that by, well, 2 seconds minus 1 second. Well, 36 minus 84 ends up being negative 48. And 2 minus 1, of course, is 1. And so the result here is a negative 48. And what is it? The top parameter is feet off the ground, so it's feet per, and the time is measured in seconds. Okay, so the average rate of change, or the average velocity from 1 second to 2 seconds, is negative 48 feet per second. And that negative is indicating that it's actually going down instead of up. Okay, part B, find the average velocity from 1 second to 1.5 seconds. So there's a couple of pieces of information we need. See, for t being equal to 1 second, we've already calculated the height to be 84. When t is 1.5 seconds, we know that we're going to need the height for that. And so we just put it in the formula. H is equal to negative 16 times 1.5, in this case squared, plus 100. And when we do that calculation, we end up getting a 64. So now here again, this is the way we're going to do this. See, this is like the A value, and this is like the B value. See, our later time is B, our earlier time is A, from A to B. So this value is like the F of A, and this value is like the F of B. So remember how that goes. The average rate of change, which in this case is the average velocity, is F of B minus F of A divided by B minus A. and f of b is 64 minus f of a, which is 84, divided by b is 1.5 minus a, which is 1. So that ends up being negative 20 in the numerator and 0.5 in the denominator, which is a negative 40. And of course, again, it's feet per second. So the average velocity between 1 and 1.5 seconds is negative 40 feet per second instead of the negative 48 feet per second we saw earlier. Okay, part C, find the average rate of change, or excuse me, the average velocity from 1 second to just 1.1 seconds. So we go through this idea again. When t is 1, we have an h that is 84. When t is 1.1, I've gone through and already done the calculations, and putting it in to calculate h, I get 80h in this case is 80.64. 80.64. So when we calculate the average velocity, okay, that's f of b minus f of a divided by b minus a. And remember, it's from a to b. So again, this is the f of a value, this is the f of b value. So in this case, f of b 80.64 minus f of a 84 divided by b 1.1 minus a 1. And when we do this calculation, we get negative 33.6 feet per second. But once again, the negative is for going down. You see, at this point, we're traveling average rate of speed or velocity, 33.6 feet per second. And notice it's a very short time interval, just between 1 and 1.1. So what's happening is that we're seeing that the smaller we make the difference in time, the closer the two times get together, then what we're actually getting close to is finding out the velocity that we're at exactly at 1 second. I mean, but the average between 1 and 1.1 ought to be real near what the actual speed is when we're just at 1 second time. And that's kind of the idea of the next concept. Okay, like I said, we're changing here. Instead of talking about an average rate of speed, or a rate of change, pardon me, we're talking about an instantaneous rate of change. And so this is back to the original discussion. The average speed, we'll replace that with rate of change. The average speed over a distance is different than the speed at an instant. And so that's really what we're wanting to know here is what's the rate of change at an instant. So here's the definition. The instantaneous rate of change of f of x at x equal a. So that's not between two times or between two x values. It's at the specific time of a or the specific location of a. And this is how we calculate it. It's the limit of the fraction f of a plus h minus f of a divided by a plus h minus a as h approaches 0. Now I've written that down, that here is the result. Here's what it looks like when we get finished doing the algebra in the denominator. So if we have an a plus b and we subtract a, excuse me, an a plus h, I'm sorry about that, that's an a plus h. If we have an a plus h and we subtract a, we're left with just h in the denominator. Of course, the numerator hasn't changed. So this is the definition of instantaneous rate of change, but here's the concept. Notice that we're talking about between a and a plus h in the denominator, and we're letting h get very, very small. And so as h gets very, very small, we're getting a point that's close to a. See, we have a, and we have another x value that's close to a because the h is getting small, a plus a small amount. So we think of those two values. And so up here, we're thinking about a starting y value and an ending y value. But you see that those are getting close together. Well, anyway, we'll go with this definition, and we'll go back to that original free-falling object idea. So let me, free-falling object. And remember, the formula we had was h is equal to negative 16t squared plus 100. So what we want to know in this case is what is the instantaneous, okay? What is the instantaneous velocity which is a specific rate of change at x equal 1 second. Now, when you're talking about an average rate of change, you're talking about from one x value to another x value. But when you're talking about an instantaneous rate of change, you're talking about one specific time or one specific x value. So we have to set up a limit here, okay? And the limit looks like this. It's the limit of f of, we've already seen this, a plus h minus f of a, all divided by h as h approaches 0. Now the a, in this case, is that 1 second. See, that is the a value. So what we end up with is the limit of f of 1 plus h minus f of 1 divided by h as h approaches 0. Now, I haven't made it real clear either. I'm using the function notation, but remember, this is just the h value. That's just an h, and that's the h value specifically, okay, when time is equal to 1 second plus just a little bit more. See, h is an amount that's getting smaller. So this is the h value when t is 1 plus h. This is the h when the time is exactly 1. So before we can calculate these limits, we need to know those pieces. So when t is 1 plus h, then of course h, and actually it's a different h in this case, and it's kind of confusing, isn't it? This is let me put it as the height, okay? This is actually the height h. This h down here in the limit is something else, okay? So this is actually the height. I'm sorry that I made this confusing. So the height is calculated as negative 16, and our time in this case is t plus h. So that's a little calculation to do, but when we square t plus h, 1 plus h, when we square 1 plus h, we'll get 1 plus 2h plus h squared. And don't forget the plus 100 out here. So that's negative 16 minus 32h minus 16h squared plus 100. And we can combine the 100 and negative 16 and get negative, 84 minus 32h minus 16h squared. So this is really the f of 1 plus h value. Now, when t is just 1, then the height that we have, we calculate that, it's negative 16 times 1 squared plus 100, and we already had that before. That's negative 84, isn't it? So this is that f of 1. That's the height after 1 second. Up here is the height after 1 plus h, which that's just 1 plus a little bit more, because remember h is going to 0. So we go back to our problem now, and the instantaneous velocity. I'm having little difficulties here, aren't I? Instantaneous velocity is the limit that we saw set up there. The limit of f of 1 plus h minus f of 1 divided by h as h approaches 0. And we calculated, see, the f of 1 plus h was negative 84 minus 32h minus 16h squared. And subtract f of 1, which was a negative 84. And that's all divided by h, and as h approaches 0. Well, on top, when we simplify that, notice we're going to have a negative 84 and a plus 84, so we're going to be left with negative 32h minus 16h squared, all divided by h, as h approaches 0. Now, we can't substitute an h in, but what we can see is that in the numerator we have a common factor of h, so we can actually simplify this expression. That h will factor out, and we'll have a negative 32 minus 16h left there divided by h. And so now we can cancel the h's. And so we're looking at the limit of negative 32 minus 16h as h approaches 0. And here we can do a simple substitution. We can say, oh, that's negative 32 minus 16 times 0, which ends up being negative 32. And of course, this is feet per second. So the instantaneous velocity at 1 second time passed is negative 32 feet per second. And if you look at the previous page, you saw that the average rate of change between 1 and 1.1 second was negative 33.6. And so you see, as we reduce that time difference, we're getting closer to that negative 32 instantaneous velocity at exactly 1 second. Well, that is going to end my discussion of instantaneous rate of change and average rate of change. And as you see here, the biggest part of this had to do with average rate of change. We'll come back and see instantaneous rate of change or instantaneous velocity a little later on.